Welcome everybody to our last session of discrete optimization talks for the semester. We will be back in the next semester as well, but for this semester, we're very happy to have two wonderful speakers, Robert Hildebrand and Ruth Misner, to wrap things up. We start off with Robert. And Robert is an assistant professor in the Grado Department of Industrial and Systems Engineering at Virginia Tech. He obtained his PhD in 2013 at UC Davis under the supervision of Matthias Koppe. Apologies for the mispronunciation. Afterwards, he spent 2 years in Zurich as a postdoc under Robert Weismantel, I believe. Subsequently, he was a Goldstein Fellow at the IBM Watson Research Center, and then he also participated at the semester-long Simons Institute on bridging continuous and discrete optimization at UC Berkeley. He's interested in mixed integer nonlinear optimization, cutting point theory in practice, redistricting more recently, stochastic scheduling, and machine learning. So, Robert, we're very excited to have you here. Thank you for joining us. The floor is yours.
Great. Well, thanks for having me. It's very exciting to talk here. So I'm going to tell you today about this paper, Compact MIP Formulations in Quadratic Programming. And this is joint work with Ben Beach, PhD student at Virginia Tech, and Joey Huchette at Rice University. So we're going to look at quadratic programs. I'm going to tell you like the basic setup here, and then we're going to focus really just on like a MIP formulation of a simple nonlinear equation here. So here's one approach for solving quadratic programs that you might consider. We'll look at a quadratic objective. I want to really think about something being non-convex here. So convex things are nice. We'll stick non-convex. They're very complicated. We'll have linear constraints. You could use different constraints if you want. We'll just talk about linear today. And there's this idea that's been used for a number of years of this like diagonal perturbation. And so the idea is we're going to take our quadratic matrix here and perturb it by some diagonal matrix D. And the goal is then make this term convex so that you can try to convexify the whole objective. And now what you have to do is then subtract off the bit that you didn't want somehow. And what we'll do is we'll linearize that bit, and we'll just push that into constraints as these yi's equals xi squared. So it's nice you don't have any bilinear terms to deal with, and you just focus on these n different equations, yi equals xi squared. And if you do the diagonal perturbation a certain way, you maybe have fewer of these equations to have to deal with. So I'll point out this was called the quadratic reformulation method, or quadratic convex reformulation method, developed in the 70s from Hammer and Rubin. And there's been a number of papers following this in recent years that talk about the theory or different ways to do these things. And I'll mention kind of the goal of this. So one way to do this is you want to say, how do I perturb using diagonal matrix such that this is then positive semi-definite? And then you know your quadratic is convex. Okay. And then how might you do this? A few approaches have been taken. Well, you could say, let's do a diagonal matrix that's got the same value on every entry. So just use like a minimum eigenvalue for perturbation. Or you could say, well, let's use something more complicated and have a different value on every entry. And here you get like an SDP to solve to try to find a nice lambda for this. There's also been some approaches using Lagrangian, so you include constraints to try to perturb the objective. Or you could say, let's do a full eigenvalue decomposition of the objective so that you really look at the space where you have the concave terms that you want to get rid of somehow. And that's great in instances when you have few concave terms. Okay, so lots of ways to do this. What I want to do today is really just focus on this equation, y equals x squared. And so we're going to try to get rid of this non-convexity, and we'll use some piecewise linear approximation, which will result in then some convex MIQCP in the end. Okay. So I have quadratic objective, mixed integer constraints that should model the whole thing. I'll say this approach is kind of closely related to a paper from Dong and Luo from 2018, and somewhat related to work from 2011 from Saxena, Benami, and Lee. Okay, so that's the basic setup here. There's a ton of literature that I should probably rant on about for hours, but I should just mention, there's lots of literature on approximating nonlinear functions with piecewise linear approximations. Recent work has looked at using neural networks for these things. And then this is a very short list, which should be a very long list of MIQCP references and QCQP references you might look at. So lots of other approaches to handle these things. We're just going to focus on this one idea today. Okay, so how do we model y equals x squared? So I'm going to recap what Dong and Luo did a couple of years ago and kind of show you their MIP formulation, and then we'll get into our approach to handling this. So they have a nice MIP formulation here, has lots of sines and cosines, and what this models is that you have the y equals x squared curve here in this yellow piece, and what you can see is that there's a parameter here that says how many levels do I want to use to get a closer approximation. And so I believe the parameter is new, could be d, but I think it's new here, to where if you set the parameter to be 0, you can get basically the convex whole, or a McCormick relaxation of the quadratic. And as you increase this to say 1 level, you can get a union of triangles here, these blue regions, or 2 levels would get you down to these little green regions, which as you see is a much closer approximation of y equals x squared. This is the type of approximation we're going to go for. I'll show you the idea here, which I think is really cute. So they use this Yarotsky formulation of the second order cone. So you do this polyhedral approximation, and the idea is that you can have a small formulation that gets you exponentially many inequalities to make a nice approximation of the cone here. And what you can say is, well, if you take a slice of the cone, you really get a quadratic function sitting in there. And so if you then say, well, let's take a slice of this polyhedral approximation, well, then we end up with a nice piecewise linear approximation of y equals x squared. Okay, so a nice way to turn this idea into something in just 2D here to get the piecewise linear approximation. There's some other work in the paper, obviously, to get the upper and lower bounds and talk about other aspects of this and computational results. That's kind of the nice idea of how that comes about. Okay, so it turns out y equals x squared has a lot of structure to it. And if anyone understands how these two ideas are related, I'd love to think about this more. But so Yarotsky from 2017 had this idea of like modeling this equation using a neural network. And how this comes about, really simple actually. So you take the y equals x squared and we take a linear approximation of this curve and say, okay, we have a line. And then if we up this and say, well, let's have a piecewise linear approximation that has 2 pieces. And we'll make this uniformly space breakpoints. So we'll say, let's use the 1/2 here. And for our second approximation, we get this orange piecewise linear approximation here. So on the right over here, I'm going to track the differences between my 2 piecewise linear approximations. And I'm going to scale it by a factor of 4, just so it has a nice upper bound here. You see I have this nice triangle function. Okay. So as I go to successive pieces here, so now we have a green approximation here, which is 4 pieces. And then I look at the difference between successive approximations here, you see we get this continuing pattern here, the sawtooth function. And again, with some scaling, you see it's going by some powers of 2 here. Okay, it turns out if you continue this approximation, the sawtooth function just keeps increasing in frequency, and you can model these things in a nice way. Okay, so this brings about a recursive pattern for modeling these differences. And so you can write this as g of 0 equals x, or your first linear approximation. And then for every successive term, you can model the GI based off of the previous term in this simple sawtooth recursive pattern here. And so now your nth level piecewise linear approximation can be written as this linear piece minus some powers of 2 times your differences. Okay, so where do we jump off here? Okay, so here's a neural network picture. You could write it as a composition. But what I'd like to do is jump off and say, well, let's try to model this using a MIP, which shouldn't be too hard to do. We can define some alpha I variables to be either 0 or 1 that handle these inequalities up here. You can say we have continuous variables gi that define when the alpha is 0, 1. And we want to model this relation that the gi is either twice the previous one or twice times 1 minus the previous one.
Robert, can I interrupt with a question?
Please, yeah.
So was Yarotsky trying to show that a certain neural network can approximate y equals x squared? Was that where the came from?
He looked at that and then just general polynomials as well. And so there's kind of been a big push in the neural network community to see like what's the smallest representation you can get for certain polynomials or other functions.
I see. And that was not known. So that result is really new.
Yeah, that was not known. And at least one person I talked to was pretty frustrated that he didn't see this idea because it's so simple and elegant.
Yes, indeed. Thanks.
Okay, yeah. So let's write a MIP about this. Not too hard to read the MIP. So you have this binary variable alpha, and you can say, well, hey, if alpha is 0, then this top inequality is tight, and you get that gi is twice the previous one. Whereas if alpha is 1, you can model this and you say that gi is then 2 times 1 minus the previous one. And this gets this recursive sawtooth pattern working there. Yeah, let me know if you have questions at this point, because I'm going to talk about this model a whole bunch now. Okay, so I like this model for a few reasons. So it's very simple. See, there's just 2's in it, so the coefficients are simple. And it's not too hard to write down and read and actually implement. Some notes about this. I'll talk about some of these proofs at some point. It's not an ideal formulation, so you don't actually get the convex full of these integer points in the space here. It seems that there's exponentially many facets. We have some characterization of some of the facets right now, but not all of them. But I'm not sure if it's worth yet pursuing all those facets. So that's something to figure out. What does happen, though, is it turns out that it's sharp and hereditarily sharp. And these ideas have to do with projection into the x and y space, and then asking, do we have idealness in certain cases there? And so I'll show you how that works out. And then I'll talk about how this formulation really produces an optimal approximation in terms of area we might consider. And then we'll show some computations. All right. Okay, so Hadberg and a few other authors talked about this idea of sharp and hereditarily sharp. And so the definition goes something like this, where we're going to look at an LP relaxation. And what I want to do is project into the space of the variables that I really care about, and then ask, is the projection of the LP relaxation the same as the convex full of the projection of the integer stuff? And so you have this like integer formulation up here, you project it down, take the convex full. Is that the same as the projection of the LP relaxation? So that's what we'll call sharp. And then we'll talk about hereditarily sharp, which in my mind has to do with branch and bound. So suppose that you're branching and fixing some of your integer variables along the way. So you take a handful of them and you fix them. Does this property still hold if you look at the extended space, fix things, look at the IP and project it down, and then take the convex whole? And it turns out that's going to be the case for our model here, that the LP relaxation is somehow really strong and it preserves the strength as you continue to branch. Okay, so let's talk about sharpness proof. This is 2D geometry, so it's easy enough to think about. So you think about the MIP relaxation is really this red piecewise linear function here. And then the convex hull of that is this yellow region here. And what we want to do is show that the projection of the LP relaxation in extended space is actually this yellow region here. Okay, so the proof idea, we say, well, let's restrict to some X line here. And then what I'm going to do is look at the max and the min that this value attains over this X line. And so if you look at the max piece here, you can show that that maximum is pretty easy, a convex combination of these two red endpoints here. So that part of the proof is pretty easy. And then on the other side, we want to say, well, if we try to minimize y along this line, what happens at this point here? And can we argue that this is actually an integral value? And so part of this is that we're going to argue that there is an alpha that makes that point integral. And the other part is that we can show you exactly what these alphas are. So for this interval here, the alpha is going to take the value 0, 1, 0. And we'll talk about some significance of the alphas in a little bit. Okay, so the proof idea, possibly a standard concept for the proof, which is look at the minimum there and then say, well, let's ask, does it have the structure we want? And we ask, well, does the GI satisfy the recursive relation with the prior GI that we wanted? And if it doesn't, then we just say, well, let's create a new variable that says, well, let's look at this GJ and say, either it's going to take this value GI here, or let's push it up to the minimum value that it should actually be taking. And so what you do is you create this new GJ tilde, and then you want to go through and check, well, do I get a lower value in Y here since you're minimizing Y? And also, is it actually feasible somehow for the system that you're making? And it turns out that the feasibility question, there's a nice little trick here to just use Lipschitz continuity and see that the difference between your your successive values of G here doesn't blow up too much when you look at the new value here. And then you can do a little calculation here and show that you actually get some decrease in the Y value if you were to try to fix this to the recursive value that you want. So what does this mean? It says, well, if all the GIs are actually equal to their recursive value here, then you can say that there's an alpha that's integral that satisfies all this, because the alpha defines which value you're taking there. Okay, so that's the idea of this proof. What I want to talk about is this hereditarily sharpness proof, or this idea. I don't think I can actually get through much of the proof. But so, let's see, do I have that picture? Okay, so here's the picture for hereditarily sharp. So suppose that we look at our alphas here, and I say, well, let's really fix the third alpha to be 1. And I like this picture because it kind of does some strange branching here that I wouldn't expect. So we're going to think about the third row here and fixing all the alphas to 1. So I'm going to throw out anything that has an alpha 0. And you see we get this new formulation here of just these red pieces. And it turns out that the projection of the LP relaxation from extended space after fixing this equation here is actually this yellow region here. And so the LP projection really somehow follows what happens when you branch here. Okay, so key idea in actually creating this proof, and possibly what's driving all this, is this idea that the binary vectors here follow what's known as the reflective gray code of doing a binarization of some integer values. So I don't know if anyone knows about reflective gray code. I didn't know about this until 6 months ago or so. So I'll tell you what that is and kind of why it's interesting. And I'll point out that there was this great paper by Juan Pablo and Shamir and George from 2010 that talked about like really powerful compact piecewise linear formulations using fewer binary variables. And it turns out they also had this reflective gray code property sitting underneath there too. So I think there's something kind of special about that. Okay, so what is reflective gray code? We'll go back to, I don't know, high school or something. We'll talk about how do we binarize integers using 0, 1s. So in my first layer here, I'm going to say, well, let's say we just have a single bit to deal with, and we can model the numbers 0 or 1 using the single bit. Okay, so let's go to 2 bits, and we can now get the numbers 0, 1, 2, 3. So what we're going to do is take this 0, 1 here, and I'm going to stack it up here as my first 2 parts. And I'm going to pad it with some zeros on the left here. Now the reflective part says I'm going to take this yellow block and reflect it to get a 1, 0 here. And then I'm going to pad the left with 1s here. So this is the reflective part. And you see it actually continues here. I take this whole block to the 3rd level, and this fits in right here. And then you reflect this block, and you have this over here, and you have the padding of 0s and 1s here. Okay. So what's really special about this is that you see that successive pieces in the code here differ by exactly 1 bit. So there's only a 1 bit change between here and here. which is not true with the standard binarization you might try to use. This is helpful in like communication and error correction type codes and some other areas of computer science, and turns out to have some nice properties here. Okay, so how does this match with hereditary sharpness? So suppose that I was going to take my second bit here and say, well, let's fix it to alpha 2 is 0. And so what I'm going to do is just remove all the other parts that don't have alpha 2, 0. And then I'm going to, let's see, I'm going to remove that column here. And there's something really interesting that after I do this, you see that the code here is actually exactly the same as the code at L equals 2 level. There's something really special there. Now, if you were to go the other way and you say, well, let's look at fixing it to 1, what happens? Well, we can reduce it just to 1s and take that out. And you see, okay, we screwed up. It's not quite right. But if I were to flip all the bits in the second column here, then I would come back to this first part here. And so there's an easy transformation that gets you back to a smaller gray code formulation. Okay, so that seems to play a crucial role in our proof of this hereditary sharpness. The proof is a bit longer than I want it to be, since there's kind of an issue here where you have to deal with these gaps between successive integer points. Since this gray spot is not actually in the bit formulation, you have to figure out how to handle that. But we try to follow the same proof as the sharpness proof, but with a lot of extra details there to figure that out. And I think driving this is this gray code idea here. Okay, I have no idea how much time I have left, but I'll keep talking here.
Okay, so about 3-5 minutes you can take.
Okay, great. Okay, so I'll mention the model we gave is really like an upper approximation. You can kind of tweak the model by just adding some error in the model that gets you a lower bound and then gets you the same kind of regions here as we talked about in the beginning. And it turns out, so you add like linear limit inequalities to get that. You can also add an extra inequality that gives you a nice cut here that cuts off in a little extra bit of the region. And so those are possibilities we want to include everything. We also have some arguments here that talk about this having like an optimal area here. So if you look at, say, the McCormick relaxation of the y equals x squared, you can say, prove pretty easily that the area there has to do something cubically with the difference between these points. And if you put this into a proof here, you can say, well, let's think about how do I establish breakpoints that really minimize the total area that I would want around my y equals x squared. And so if you put this into a little minimization problem, you can do KKT conditions and prove that this uniform spacing that we obtain is actually an optimal formulation for the number of breakpoints to minimize the area. Okay. And then lastly, if you look at a ratio of reduction between successive steps and compare this to the previous method that we looked at, what's nice is as you decrease in layers, the area always decreases by a factor of 4, whereas in the other formulation has kind of suboptimal decrease in the area as it approaches the y equals x squared. Okay, so there's some other pictures, but I'll just go through and mention some computations here and say that something's nice happening. We tried to do as thorough computations as we could. So we talk about time and gap, and then talk about like the number of best instances here, and then some timeout things. And if you forgot what we're doing, the whole point is we're looking at these quadratic optimization problems, and our examples are actually all box QP. I should say that, you know, we can apply to other types of problems as well. Okay, so we tried a lot of different things, Barron, Cplex, Groby, and we separated these results into easy, medium, and hard. And I'll go pretty quick here. So the short answer is, well, I should say Groby got better over the last year or so as we were writing this paper. So the results changed, but Groby and other things do very well on easy instances. On the medium, we tend to be a little bit competitive, and Groby and Cplex seem to do pretty great still compared to other things. And then what we found where we kind of shine is in these hard instances where basically everything times out, where we look at what's the best gap that we're getting from the different models. And it turns out this neural network approach that we're calling this seems to have get you the best bounds for these really hard instances. Right, I probably have a minute left, so I'll just throw out something I'm thinking about other than research here is I've been working on this open optimization website. So if you have lecture notes or open source material or images or something that you want to contribute to this, trying to build some collective here to reduce everyone's work in teaching optimization and writing papers and making pretty graphics and whatnot. So let me know if you're interested in these types of things. And we have a couple textbooks up there that are all open source that you can steal stuff from if you want. Okay, and there's a gallery, and thanks for listening.
Thank you very much, Robert, and thank you for these efforts also on the side of non-research. Does anybody have any questions for Robert? You can either ask them in the chat. We probably have time for just maybe one quick question right now. There will also be time to talk to Robert in a more one-to-one session in the breakout rooms at, I guess, in about half an hour.
Do you know why Gurobi got better at these instances?
Well, with Gurobi 9.0 that came out, what, a year ago or so, they started solving these non-convex problems where they weren't doing it before. And I think they've just been implementing more techniques that are from the literature as time goes on. And, you know, Gurobi's usually good at small instances too, where they use special tricks for things.
Mm-hmm. So it could be it's just a Gurobi implementation of some of the other papers, or
yeah. And I'll say that, you know, we did a very simple implementation of our work. We could do like an adaptive strategy or other types of things that you could think about.
Right.
So we haven't, you know, gone to the depths of making the best solver that we could, just trying to study the formulation as best we can.
Well, thank you. Let's thank Robert one more time. And we will transition to the next speaker. Ruth, please start getting set up. But again, if you have any questions for Robert, please stick around at the end, and we will have time for you to ask them in a more personal setting.